Welcome everyone. Let's start solving the question 1012, question number 120. So the question is given as that the potential energy diagram is shown below for ion elimination mechanism indicated reaction. So actually, first of all, it will generate the tertiary carbocation. This is 1, then transition state is 2, after that this 3, and then this is 5, and transition state is 4. Now the thing is that, wait a minute. Now, by applying the Hammond postulate to the potential energy diagram, for this reaction, which one of the following statement is correct? I will determine which of the following statement is correct. So, structure 1 of the transition state 2 is more carbocation-like than the transition state 2. So, let's see what is Hammond postulate. So, Hammond postulate states that the transition state, suppose this is the transition state 2, this is transition state will be similar like the species which is lower in energy to the transition state. Means suppose this kind of thing is possible, this is product and this is reactant and this is the transition state. So actually the transition state will resembles to the species which is closer to this energy to the transition state. So the transition state is closer to the energy to the product. So this transition state is more resembles to the product than the reactant. So like this is all about the Hammond postulate. So one can see that the second transition state is more resembles to 3. Okay. So in the first statement, the structure of transition state 2 is more carbocation like. This is the 3. Yes, that is more carbocation like. Then the transition state 4. That is not true because the transition state 4 is more closer to the 3. So the resemblance between transition state 2 and 4 with the carbocation is 4 is more resemblance with the 3 than 2. So this is a wrong answer. And in the structure of the transition state 2 is less carbocation like than the transition state 4. That is true. So the correct answer will be B. In the next question number, let's solve question number 102. So in this reaction, first of all, this substrate is given and benzoyl peroxide. This benzoyl peroxide is a initiator, radical initiator. So it will generate a radical. Most stable radical will form this place. After that, it will attack this place and it will generate this radical. 1, 2, 3, 4, 5, 6. Then it will form this CO2. 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. The other part will attach to this 7, 8, 9, 10. 7, 8. 5 contains the radical. 5 contains the radical. Then 6, 7, 6, 7, 8, 9, 10. 10 contains the double bond. Now the thing is that there is a possibility this 1, 2, 3, 4, 5 member ring formation. This is by 5 exo trig by Baldwin's rule, and this radical will shift there and it will give the product as COET. This is methyl. So this resembles to option B. In the question 103, consider the catalytic hydrogenation of the compound PQRs as indicated in the table. The number of carbocyclic ring and 5 bond present in the. We have to find the WXYZ actually. So this is compound and molecular formula before hydrogenation, molecular formula after hydrogenation, number of carbon cyclic ring present, number of pi bond present. So basically, in the first case, in the P, let's find the double bond equivalent. Double bond equivalent is equals to number of carbon, that is 40 plus 1 minus 56 by 2 divided by this is equals to 13. So double bond equals to 13. Number of carbocyclic ring means there are two large cyclic ring at present, and the number of pi bond present, pi bond is 11. So this is before hydrogenation, this is after hydrogenation. So those 11 bond will undergoes the hydrogenation, means hydrogen will add to this. Suppose this is a pi bond and hydrogen adds to it. Finally we get this alkene. So what is happening here? For each pi bond, 2 hydrogen is adds up. So there is a 11 pi bond, that is equivalent to 22 hydrogen atom. That is binds to the C40 H56. Now this is adding to the hydrogen and giving C40 and H78. Okay, so we get the answer W is equals to this. This is equals to W. So this option D will resembles to this. This is the correct answer. The question number 104. The major product formed in the following reactions is. So this is given in I2NaCO3. It will generally form, first of all, the bridge iodinium ion. So this is iodine plus. Now it is connected to this end containing OH, and this OH CO2Me. Let's consider this center. This is 1, 2, 3 clockwise 4 priority group down R configuration. And this is 1, this is 2, and 3, 1, 2, 3, 1, 2, 3 anti-clockwise. So it must be 4 priority group up. 4 priority group up. So finally we'll get this is, if we say this is in the plane, then hydrogen in up and downside this alkyl group, as this is a R configuration. After that, this will attack to this center forming the 5-member ring, and it will give the final product as this is oxygen, this is CO2Me, and here OH, and here this is iodine. Now we have to determine the configuration of this center actually. So if we simply see it, then suppose this is the iodine center. Okay, this is in the plane, hydrogen up and downside containing this whole ring system, and it final end contain O minus because base is given, and this will attack to this center and this iodine will release. Finally we'll get this iodine, and now this oxygen at the anti position, but hydrogen and down containing this 5-member ring is formed. Now alpha to this is CO2Me. Now this kind of configuration is arises. So what is the configuration of this center? Let's see. This is 1, this is 1, and this is 2, and this is 3. 1, 2, 3 clockwise 4 priority group up. This is the S configuration. If we see in this center, this is 1, this is 2, this is 3. 1, 2, 3 clockwise and 4 priority S configuration. So option B is correct. Consider the following statement: the anti-addition of symmetric reagent to the symmetric cis alkene gives the receiving mixture. So there is a famous rule. This is for anti-addition. The rule is CAR, means that cis alkene, then this is anti-addition giving racemic mixture. So for example, suppose this is a cis alkene, and we are adding B or 2. This is an anti-addition. So this bromine, this is in the plane and this is up. Now the Br minus can attack from this position or from this position. It will basically give two type of product, and both will give the racemic mixture. Now coming back to the point, so the thumb rule is like this. Now for anti-addition, CAR, and for the trans anti-addition give the meso product. Okay, and for the syn addition, this is different. For the syn addition, if we see, now this is the syn addition, CS give the meso product, and trans syn give the racemic product. So in the first statement, the anti-addition of symmetric reagent of symmetric reagent to the symmetric cis alkene will give the racemic product. So option 1 is correct. The anti-addition of symmetric reagent to the symmetric trans alkene will give racemic. No, this is the meso. That is wrong. The syn addition to the symmetric reagent, now the syn addition to the cis alkene will give the meso product, not the racemic. That is also wrong. Now syn addition to the trans alkene give the meso product, racemic product. So that is wrong. Only one is correct. Now let's start the question number 106. It is saying that which statement is correct about this. We had HBr and two products are obtained. So at low and high temperature, 1 for addition and measurement. So this problem deals with the kinetic versus the thermodynamics. So two kind of products are, it is like this. Suppose this, and this is the reactant. Now H plus Br minus. Suppose that H plus will add up to this side and generated more stable carbocation. This is plus. Now this Br minus will add to this part and giving, this is Br. This is a 1,2 product, 1,2 kind of product, and this is kinetic. And another possibility is that now H plus will add up to this side. Now here is a carbocation, and Br minus will attack to this side, and this will give Br. So this is a thermodynamic. So basically this product is more stable than compared to this one. So according to me, at the low temperature, kinetic will favor, and at high temperature the thermodynamic product will favor. This is high temperature, this is low temperature. So 1,2 addition at low temperature, 1,4 at high temperature. 1,2 addition, option C is correct. Now let's go to next question. Question number 107. The total number of 1,4 addition reaction involves in the synthesis target molecule axis in the indicated starting material is RR. So basically this nitrogen will do the 1,4 addition, as there is a 2 moles first, then it will give MEnH OET, and this lone pair again attack to this center and do 1,4 addition. So first 1,4 addition done, this is second 1,4 addition, then we will left nitrogen methyl OET. Now the Dickman kind of reaction takes place. 1, 2, 3, 4, 5, 6. It will attack this and it will leave, and the product is 6-member ring with nitrogen methyl is attached to it. From this position ring, this is CO2 ET. Now this is a CONT. When there is ketone is given, this is the acidic proton. It will do another 1,4 addition. So you will get NMe CO2 ET. This is 1 2 3 4, 1 2 3 4. After that the ring closes. 1 2 3 4 5 6. This negative charge will attack this and give the final product. Okay, here one double bond is missing, so total 3 1 4 additions occurs. Next question 108. Number 108. The major product found in the following reaction: benzene first treated with the Br2Fe. So this will give bromobenzene. This and this is a bromobenzene, and then dilute D2SO4. This will transfer D plus. So bromine is ortho-para orienting. So this is a very special kind of reaction where in presence of D2SO4 it will occupy all the ortho-para positions by aromatic electrophilic ARSC, aromatic substitution electrophilic reaction. So the final product will be, this is deuterium, here deuterium and Br. After it is treated with the lithium, it will substitute this lithium, deuterium. When we treated with the H2O, this lithium substituted by H, then final product will be this. Option A is correct. In the question number 109, the major product formed in the following reaction sequence. Here SnCl2, then water. So let's see what will be the final product. So first of all, this is a Lewis acid. It will attach to this SnCl4 and it will activate this center. Now the benzene will do the NGP kind of reaction. This can attack this place, 1 2 3 4 5 6, and this can attack this place. This is the 7 member, this is the 6 member path. But we know that this 6 member ring is kinetically and plus thermodynamically more favorable. So we'll get, now this is a 6 member ring and this bond is broken. Okay, fine. Reaction will proceed through the 6 member pathway. Now it is again this O minus, and after workup H2O will get the final product as D. In the next question number 110, consider the following: that 4-chloro-3-nitro acetophenone reacts with the sodium methoxide in the methanol slower than the 4-chloro-nitro-toluene. So let's see what kind of reaction proceed here. According in the first statement, 4-chloro-3-nitro acetophenone reacts with the sodium methoxide in the methanol slower than, let's say. So let's draw the structure. For acetophenone, this is acetophenone structure. 4-chloro, this is chlorine, 3-nitro, it's react with the NaOMe. Okay, and another is that 4-chloro-3-nitro-toluene, this is methyl, 4-chloro-3-nitro. Now the thing is that this is kind of a activated nucleophilic substitution reaction. Nu minus SUB substitution. So what will happen? This will attack to this position and this chlorine will get substituted, and the ring is activated by this electron withdrawing group. So the rate is faster for this than this, because this toluene is deactivating the ring, and this toluene will pushing the electron density by plus I effect. So the substitution is slower for this case. So first statement is wrong. 4-chloro-3-nitro second methoxide first. That second statement is right. Now in the third statement, 1 bromo 2,4-dinitrobenzene. This is a benzene. 1 bromo NO2 reacts sodium methoxide NaOMe in methanol faster than the 1,4-dibromo 2-nitrobenzene. So same reagent is given, but you can see this nitro group will will deactivate more. So in the substitution reaction, the rate of reaction is more for this compound than this, because when reagent is coming in this place, only one nitro group will activate it, but here two nitro group will activate it, the ring for the nucleophilic substitution. So option 3 will also write. So correct option will be C, 2, 3. The question number 111. The most reasonable cyclohexadienal cation intermediate involved in the mechanism following isomerization reaction is. So here given HCl and Lewis acid. Different kind of cations are given. You have to find which intermediate will give this product. So first of all, in presence of HCl, the protonation takes place, and this will from this is H plus and this side, so CH3 whole 2, and this is CH3, this is plus, and this, now this is a CH3, this is a CH3. The next step, the hydrogen here, it can do 1, 2, 3, 4, 5, 6, 1, 2, it can do 1, 2 shift, and will generate this CH3 whole 2 plus, and here is double bond CH3, and this is a double bond, and this kind of structure. Now there is a possibility of migration of this methyl group, then the double bond shift to this. So this is a sigmatopic shift kind of reaction, and here this is it, and positive charge CH3 whole 2. Now from this we get the final product. So C is the correct answer. The question 112. Which one of the following reaction does not follow the addition elimination pathway? So in the first system, this will add to the system. This is 1,4 addition. Here is bromine SPH. Now OET. Now when it is reverted back, it will release. So A will follow. In the next reaction, this O minus will attack to this center, and cyanide minus will eliminate it. So this is also true. This is SNAR mechanism. Similarly, this is also SNAR. So in presence of NaOH, this will take up the proton, and it will attack to the ortho position, and that electron will delocalize to the ring system and towards the NO2. When this NO2 will pushes back the electron density, this SO2 will release. So finally we get this. This is intramolecular SNAR reaction. But in the D, this HNO2 will convert this to N2 plus, and it will form the benzene. Okay, this benzene, and this PHN3 in double bond in here double bond in minus plus, it will adds up to this by pericyclic pathway. So that is not a addition elimination mechanism. So option D is correct. In the question number 113, the number of sp3 and sp2 carbon respectively present in the Messen-Meyer complex formed in the following reaction is or are. Let's see, 2,4,6 dinitro-anisole. This is OCH3 2 4 6. When we are treating with the NaOET, the base. So what will happen in this reaction? It will attack this position and form the Messen-Meyer complex. So how it is takes place? So this is O bond CH3, then O bond CH to CH3, and there is negative charge, and here NO2, and here double bond NO2. Now the thing is that Na will attach to this counterpart cation. So the number of sp3 and sp2 carbon atoms are present. Now calculate the sp3 center. Okay, So this is sp3, this is sp3, this is sp3, this is sp3. So total will be 4 sp3, 4. Now sp2 carbon will be, this is sp2. Now using another color, this is sp2, this is sp2, this is sp2, this is sp2, this is sp2. So total 5. sp2 is 5 and sp3 is 4. Option B is correct answer. The next question, the major product X and Y formed in the following reactions are, okay, mixture of cis and trans. In the given problem, this is an example of pinacolon rearrangement. So this OH2 plus, it will leave, there is CH3, then OH. In presence of acid, it will generate this CH3 plus, and there is OH and here is CH3. So when this will shift, question number 114, we have to find the major products. This is actually a example of pinacolon rearrangement. So the whole things depends upon the migration ability. Of different group. First of all, the aryl, that is aryl contains the, this is group OMe, this is electron donating group. It has more migration tendency. It also contains the phenyl one. After that 3 degree, 2 degree, then 1 degree. This is alkyl end, and after that CH3. Now in the first problem, this OH2 first leap, there is a CH3, here OH, then CH3. In presence of H plus, will generate this carbocation. This is a tertiary carbocation, and here the CH3, here OH. When this lone pair is delocalized to it, now it will migrate. So there is two migration possibility. One is this alkyl methyl group, and another is this alkyl group, that is 2 degree. So the migration tendency of this ring is higher than comparison to CH3. So finally it will give a 5-member ring, okay, and containing this CH3, then this is COCH3. This is the final product. In the next problem, we know that the migration OH, and similar way after leaving, this will generate the, after leaving of water, it will generate the carbocation. Now between pH and between alkyl, we know that pH have higher migration ability. So this phenyl will migrate to the center, this center. So when this lone pair got delocalized, this is migrating, this phenyl will migrating to this point. Now you'll get this product. Now this is a phenyl. So option D is correct. In the question number 115, which one of the following 1,2-diol is least reactive for the acid catalyzed pinacolon rearrangement? So there is a possibility of pinacolon rearrangement. We have to find which is least reactive to it. So first of all, in the substrate, if this water got released, we get a tertiary carbocation and also stabilized by phenyl resonance. In this sense, when this group will release, there is also a 3 degree carbocation, but this group will destabilize the cation. Here no stability, here stability is there, similar phenyl resonance and hyperconjugation by CH3. In this case, if this group will release, then it will also generate a 3 degree carbocation and phenyl resonance will stabilize the system. So all three have equal tendency, not equal, but have good tendency to do pinacolon rearrangement except this. So option B is the correct answer, because this carbocation, this after leaving, this is PHCF3 plus, this is OH, this is CF3 and CH3. This carbocation is unstable due to the presence of this electron withdrawing group. So option B is correct. In the question number 116, the reactive intermediate 1,4 that likely to be formed in the reactions. So we have to find that. Now in the given reaction, first of all, H plus is given. So this is given substrate. We have to get this product in presence of acid medium. So what is the sequence of intermediates are formed? So first of all, as this is in the solution phase, so solvolysis will occur. This chlorine will release. Now this is final OMe, and this is 2. Okay, fine. And here is the carbocation. After that, this lone pair will conjugate it to the system and give this. Okay, this is methyl and double bond OMe plus. And at the next step, this double bond, using another color, this double bond will broke in this side, and this will shift to this, and it will shift to this, and it will shift to this. So the final situation is, now it will again regain the aromaticity, OMe, methyl, and here it is forming this and leaving this carbocation, and this species is 1. Okay, so these two options get eliminated. So this is one species. After that, this is proton, and it can eliminate it to give the product. This is OMe, and this. So this is resembles to 4. So 1 4. This option is possible. Option D is correct. So let's see the whole mechanism. So after that, in presence of H plus, this will abstract the proton from this side and will give OMe. This is plus, double bond this. Now this and this, when this intermediate is formed, so the correct answer will be D. In the question number 117, the reactivity order of the solvency of the following compound in acetic acid. So the reaction is kind of this is a good leaving group. This will leave, and in the polar medium, this is a good leaving group. So this pi bond will act as a NGP agent, so it will help assist the SN2 reaction faster. So in this scenario, in the case 1, this kind of attack is possible, and it will give the faster rate of product. So 1 is the highest, so option D is the correct. After 1, there is a 3 as pi bond is involved being here, and in this case the sigma bond is involving, but more than a sigma, the pi bond NiG is high, and it can act as a beta homo. So that's why this order will be possible. In question number 118, which one of the following statement about the indicated reaction is order correct? HBr is given major product form. So this HBr will generate OH2 plus, but the thing is that it will, if it release, it is a 2 degree carbocation, so it can goes through SN2 or SN1. But this bromine lone pair is present in the anti-periplanar arrangement. Let's see, if we push this bromine in the plane and this OH2 plus like this, now this methyl up, now this bromine lone pair will attack in the anti-periplanar arrangement, and this will generate a bridge bromonium kind of intermediate, and both the methyl in the upper side. Now the Br minus will attack from this anti kind of thing, and will generate this bromine. This is up and this is up. Now it will resembles to option 1, and the question is, it is a chiral or achiral. So if we move this methyl cis to each other, this methyl cis to each other, then this bromine and bromine got trans. So in the Fischer projection, If it's CH3 bromine. So they are a chiral one. So according to me, the answer B will be correct. Major product of the reaction is 1, and that is a chiral. In the next question, 119, the major product found in the reaction 1 and reaction 2 are reaction first 1 or 2 are 2 bromocyclohexane 1 all H plus, and what is the product and what is the product. Okay, let's see. First of all, draw the reactant. 1 or 2 are 2 bromocyclohexane. This is a cyclohexane. 1 all 2 bromo. 1 or 2 or. This is our configuration. So 45 degree group down 1. This is 2. So it will be 1, 2, 3 clockwise. 45 degree group down means this OEG is up. That is our configuration. This is 1, this is 2, this is 3. 1, 2, 3 anti-clockwise, and to get the R, so we have to put hydrogen in the up. So the final thing will be this is OEG in up and bromine down. Now if we draw in the shear conformation, the bromine and OH, this is OH and this is bromine. In presence of proton, AOH2 plus. Now this bromine will attack and from bridge bromonium ion, and this is bromine plus. Now all the products are the dibromo cyclohexane, so Br minus has possibility to attack both, but this is a kind of a, this bromine is down, mean this hydrogen, this is a equatorial attack and this is a axial attack. For better understanding, the attack will proceed in that direction. So that's why the axial attack is favored over the equatorial. So final product will be this is bromine and this is bromine. Now the configuration of this fixed means this is R remains, and in this scenario this is also R. In the second case, this is 1s 2r. 1s means this OH in the down, and 2r, this is also bromine down. If we draw the cyclohexyl, okay, this is OH and this is bromine. So there is no possibility of NGP, that is not possible. So this is for this follow normal SN2 mechanism, means the Br minus will attack from the equatorial position and release this. So finally we will get this product, this bromine equatorial, this OH also equatorial. So the final will be 1, this is 2, so hydrogen, 3, 1, 2, 3, this is clockwise, 450 group down means R configuration. And for the bromine, this is 1, this is 2, 1, 2, 3 anti-clockwise and 450 group up, that is also R. So both are R, so the final answer will be D. In the question number 120, in the solvolysis reaction 1 and 2 in the aqueous ethanol, which one of the following statement is or are true? So the comparison between these two, let's draw it in the cyclohexyl from this chlorine is up and this pH is down. In the solvolysis reaction, this sulfur will attack in this position, that is by NGP, and this is sulfur and pH. So the rate of reactivity of 1 is higher than 2 because in the second scenario the NGP is not possible. 1 react faster than 2 and major product are, so in the major after that the OH2 will attack from this scenario and give the OH in the up this product. Okay, so this will give this product. So 4 is the major product, 1 react faster than 2 and 4 is the major product. Option B is right. Thanks for watching this video.